All right, there we go. So back to polar coordinates. I mentioned the other day that changing between polar and rectangular is a lot like converting from feet and inches to meters and centimeters. Why bother? Just pick one and stick with it. The main thing is choosing the right coordinate system for your problem. And often it's tough to know what the right coordinate system is. So what that means is, for now, since we're new at it, we're going to have to remember the connection between those two different worlds. So the main connection is this right triangle right here. If that's theta and that's r, and different color, and we know usually vertical is y, horizontal is x, then we get the following relationships. X is equal to r times the cosine of theta. Y is equal to r times the sine of theta. Other ones, r squared equals x squared plus y squared. And the tangent of theta is equal to y over x. Okay. So those are going to be pretty useful for us for now. Another thing to notice. Here, I've written x as a function of r and theta. When we're working in polar coordinates, we generally consider r to be written as a function of theta. Okay? For example, in class the other day, we let r equal, I believe it was the cosine of theta, and we took a look at what the graph of that was. We ended up with a circle. So if you think about differentiation, and you wanted to differentiate an equation like this, well, here I have x as a function of r and theta, but r is generally going to be a function of theta. So we have to differentiate implicitly on both sides when something like that comes up. So I just want to consider, what would a derivative of x look like? What would a derivative of y look like if the independent variable is theta? And we'll talk about what all this means. So consider the equation. X equals r times cosine of theta. And what we want to do here is differentiate with respect to theta. So if we differentiate on the left side, well, the derivative of x with respect to theta is just dx d theta. On the other side, r is considered to be a function of theta. Obviously, cosine is a function of theta. So we have the product rule acting there. And so the product rule on that side says, let's take the derivative of r with respect to theta, leaving the other function alone for a moment, and then add that to r times the derivative of the cosine of theta, which is negative sine. Cleaning that up a little bit, we get dx d theta is dr d theta cosine of theta minus r sine of theta. Similarly, if we did that to the equation y equals r sine of theta, we'll get dy d theta is equal to dr d theta times the sine of theta plus r cosine theta. And it turns out these are going to be important relationships. Oops, missed part. Let's do that. These are going to be important relationships here. Sometimes I'll abbreviate dr d theta as r prime. Usually a prime means derivative with respect to x, but when we see r, we should think theta. But you'll often see an r prime, and r prime is going to mean dr d theta. Okay. All right, so we'll come back to those in just a minute. Let's go back to the polar world. Because we have so much familiarity with rectangular coordinates, even when we're working in polar, we'll often make an XY axis to give ourselves some bearings to work with. In particular, because polar coordinates depends on a pole, some central point. Okay, that central point is also the origin in XY coordinates. And we graphed a circle the other day, looked like that. R equals the cosine of theta, where that is 1 over there on the x-axis. And we created this graph as R went from 0 to pi. What if we let R go from 0 to 2 pi? We didn't go that far. I wonder what would happen. Let's just double check. So let's create a few more points extending what we did in class the other day. We stopped at pi. So right after pi, let's see, the next angle would be 7 pi over 6, I think. You guys got that trig cheat sheet? I think I posted a link to it back here, or that polar cheat sheet. I think it has 12ths on it. Where did I put it? I put it in right here, polar angle scale. Yeah, so I'm not going to work with 12ths too much, but once in a while we will have to. Today we're going to have to. But 7 pi over 6 is the next angle I would work with. And cosine, remember, is the x value here. So at 7 pi over 6, where x value is going to be negative, and it's going to be square root of 3 over 2, which is about 0.87. Is that what we found the other day? So at the angle 7 pi over 6, x is going to be approximately negative 0.87. So let's think about where that puts us. 7 pi over 6 means point in that direction right there. But the negative radius means head the other way. And so it's going to throw me up there on the curve. So what's going to happen is as I range from pi to 2 pi, I'm just going to retrace this curve again, over and over again. So this circle from the equation r equals cosine theta is a periodic function. What's the period here? How often does it repeat itself? Pi, yeah. Polar coordinates is a bit trickier than rectangular coordinates. In rectangular coordinates, y equals cosine of x, the period is 2 pi. In polar coordinates, r equals cosine of theta, period is pi. Okay, and every function requires a little bit of exploration to try and figure out what its period is. So we'll take a look at a couple others in a minute. Let's see, what else should we look at? In rectangular coordinates, if you did something like multiply on the outside, that was a vertical stretch, remember? Okay, now there isn't vertical and horizontal here because R is neither vertical or horizontal, it's just the distance from some central point, right? So if we do a multiplier in front, like what if we looked at, oops, new page, R, oops, wrong R, fussy technology, R equals twice the cosine. Come on. Oh, there you are. So for graphing, if you have a portable graphing utility, hopefully it can do polar, otherwise Geogebra is a good tool. Twice cosine of theta. So we're going to play around with both tools and plotting points to kind of figure out what's happening with these suckers. So did I say Geogebra? I lied. Desmos. Geogebra is not helpful for graphing polar functions, but Desmos is. All right, so for Desmos, if I just type something like R equals cosine theta, it automatically changes it and assumes I want polar coordinates, and it graphs that circle we looked at earlier. I can zoom in on it. What about R equals twice the cosine of theta? What does that appear to be? Another circle, but the radius is bigger. So what we're stretching in this case is the radius. And here the radius means the distance from the pole to whatever point we get to. Okay, so we stretched out. Here the radius was up to there, now it's out there. Radius used to be square root of 3 over 2. Now it's square root of 3 over 2 times 2, which is square root of 3. Okay, so we're stretching each of those radial points as we come out. Okay. Another thing to think about, if we added something like, if we started with x squared and then inside we put an x plus 2 and then squared it, what did the plus 2 do to the graph in rectangular coordinates? It's a shift, right? Left to right. And it was kind of counterintuitive. It went the other way. So x plus 2 inside the function took us to the left, x minus 2 took us to the right. Okay. Now, remember, polar coordinates isn't left or right. It's about rotations and distances to the center. So what do you think is going to happen if I add a number inside? So if we look at r equals the cosine of theta plus something. Any guesses? What does theta represent? An angle, right? What do angles do? They turn. So what do you think is going to happen if I add something to my angle? Let's check it out. Ooh, what just happened there? Make that 2 a 1. Make that 2 a 1/2. We have something even better. Let's make that 2 an a and make a slider for a. And then watch what happens as I move the slider. So what is a doing when I add it inside of the function? It's causing a rotation, which makes sense because isn't theta an angle and an angle is a rotation? Yeah. And here, as the angle plus a positive angle, it shifts us in a negative direction. Just like with rectangular functions, x plus 2 shifted us to the left. So if I wanted this to rotate in a positive direction, I would have to do theta minus whatever angle I want to rotate by. And so now as I increase that a, that rotation amount, I can come around. Pretty cool, huh? Gets even better, watch this. Kind of fun, huh? All right, Geogebra. Desmos is pretty awesome. I was so impressed when they added this. Okay, so kind of fun stuff. Let's look at another one, and I think we've had enough of these guys. Oh no, A can stay there. Okay, and let's take a look at what happens if I double the angle. That's different than a rotation. That's like theta plus theta. Theta is a variable. So this is kind of beautiful. Okay. So once we do a multiplier of the angle, then the thing folds in on itself, which is kind of wild. So what we need to do next is we need to kind of trace out what's happening here. Okay. Adding a number, by the way, is just going to rotate the flower. So if we add something to it, and this is cute, and we run it, it's just going to spin around. Okay, it's the same shape. It's just different rotations of it. So I mentioned before that choosing a coordinate system is dependent upon the problem. So if I have a problem that requires me to shift things left, right, and up and down, I want to be in rectangular coordinate system. If I have a problem that wants me to rotate stuff, I want to be in polar coordinate system, much easier. Okay. Sometimes it's depending on what we're doing with the object. Sometimes it depends on the object itself. Like circles are slightly easier in polar coordinates than they are in rectangular. On the other hand, lines are easier in rectangular than polar. We'll take a look at that next. Let's do a quick graph of this. Let's see, we looked at that graph. That would be just a circle, radius 1, center, got stretched over to 1, 0 in polar. Now we're going to take a look at r equals twice the cosine of theta. So if you have the polar graphing paper I gave you the other day, whip that out. You're going to need it here. No, I put the 2 in the wrong spot. Oops. I want the cosine of 2 theta. There we go. We know what it looks like, but we need to see what its what its period is. So polar paper is back here. And let's get a screenshot of that. Okay. So I think after we plot like half a dozen points, we'll have a good sense of how it's behaving. So I'm going to do theta first and then r. So if theta is 0, cosine is 1. And I think I'm going to take the same approach as before. I have this particular piece of graph paper has 10 concentric rings, so we can treat those as tenths. So we can let the last one be 10 tenths. So that would be theta equals 0, r equals 1. I'm going to leave a little space, and I'm going to do pi over 6, because I'm pretty sure I'm going to back up and have to do pi over 12 next. So let's see, pi over 6. If I double that, I get pi over 3. Cosine of pi over 3, my recollection, is 1/2. So pi over 6 is this radial, is this angle right here, and 1/2 would be what? 1, 2, 3, 4, 5. That puts me right there. And then usually what would I do next? Pi over 4 would be next. If I double pi over 4, I get pi over 2. Cosine of pi over 2 is 0. So suddenly we went bang, bang, boom, we're back at the origin. I'm kind of curious as to what happened in between. Like I'd like to find something in between 0 and pi over 6. And so pi over 12 is a good candidate. So I'm going to throw that one in there now. If I double pi over 12, I get pi over 6. Cosine of pi over 6 is square root of 3 over 2, which is about 0.8687-ish. Pi over 12 would be right about this angle. And so 0.87-ish is going to be right about there. So what's happening here is I'm heading out from this, out from this point, over and through and down. And so this is the direction that I'm flying through there. So let's see, this ended up being what, about 0.86-ish. This was 0. Next angle we would choose would be pi over 3. Cosine of 2 pi over 3 is negative 1/2, I'm pretty sure. Does that sound right? Cosine of 2 pi over 3. That would be this angle, yeah, negative 1/2. And where am I? Pi over 3 is this direction right there. And I just got a negative 1/2. Did I do that right? Doesn't seem right. Which means head backwards. Oh. Somehow I feel like I have a mistake here. Pi over 3 times 2 is 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. That means head back this way 1/2. That can't be right. Okay, where did I screw up? Nobody sure? Anybody get a calculator excited to help me out here? Oh, you have a calculator. Did I do my calculation right? That's right? Okay. Why does that not look right to me? Pi over 3. It's right there. Negative 1/2. Oh, I'm sorry. Yeah, no, this is right. If it was positive 1/2, that would put me out here. Negative 1/2 means go this way. Yeah, no, it's right. I don't know why I was confused. 1, 2, 3, 4, 5. Yeah, that puts me right there. So we're continuing the spiral through here. All right, next would be pi over 2. 2 times pi over 2 is pi. Cosine of pi is negative 1. So this would normally be pi over 2, but we have to go in a negative direction, which is going to put us down there. So I'm just going to make a note. That happened at pi over 2. And if we keep going, what we're going to find is we're going to get half of one of those flowerets every how many units? Pi over 4. So if I go from pi over 2 to 3 pi over 4, that will take me back to the origin. 3 pi over 4. Pi over 4 got me there in the first place. And then from there, we're going to head out in this direction. And that'll put me at pi. Just to double check, if I plug in pi, I get cosine of 2 pi, which is 1. And so that's going to put me right there. Okay. So how much of the flower have I filled out up to pi? A half of the, yeah, so what do you think the period is going to be here? Yeah, so the period is going to be 2 pi, yeah, is what we'll find. So this will take us to, let's see, 3, 4, 5 pi over 4 will take us back to the origin. And then 3 pi over 2 will take us up to the top here. And then, let's see, 5, 6, 7 pi over 4 will take us back to the origin. And then finally, 2 pi will take us back here. So the period here is 2 pi. All right, let's do one more of these and we're going to do some calculus. And we could spend weeks on polar graphs, but we're only going to take a little snapshot of it. What if I did something like r equals cosine of 3 theta? So first thing I'm going to do is I'm just going to graph it in Desmos. So I'm going to put a 3 there. So notice with the 2, I got 4 petals. With the 3, I get 3 petals. What do you think is going to happen if I put a 4 theta in there? Eight petals. Yeah. How about a 5? 5 petals, yeah. If it's an odd number, you get that odd number of petals. If it's an even number, you get twice that number of petals. Okay, kind of weird, just the way things work. So let's back up and take a look at 3 and take a look at what the period of that is. So we're going to do a sketch by hand of that one, and then we're done sketching by hand for a while. So back here. Huh, that's weird. There we go. All right, so we'll just have to plot a few points to figure out what's going on here. So theta and r, if we start with 0, cosine of 0 is 1, so we get that same starting point out there. Next common one is pi over 6. 3 times pi over 6 is pi over 2. Cosine of pi over 2 is 0. Uh-oh, we better do something in between there. So I got to sneak in a pi over 12. So let's see, pi over 12 times 3 is pi over 4. Cosine of pi over 4 is the square root of 2 over 2, which is about 0.7. So pi over 12 would be this line here, and 0.7 is about right there. So it looks like our leaf gets made a little quicker than before. Okay. Let's see, pi over 6, then we would usually do pi over 4 next. If I take 3 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, cosine is negative 0.7-ish. Let's see, pi over 4 is this angle right here, but we need to go negative, which would be in this direction here. Negative 0.798 would put me right about there. And then what do we usually do next? Pi over 3. 3 times pi over 3 is pi. Cosine of pi is negative 1. So pi over 3 is here, but we need to head in a negative direction. So that would put us right there. So from 0 to pi over 3, we just graphed 2 halves. So essentially, we've graphed a whole leaf right now. Right? 2 halves makes a whole. So if we made 1 leaf from 0 to pi over 3, how long is it going to take to make 3 leaves? Pi. Yeah, so the period here is pi. So just some things to note that we discovered here based on looking at Desmos and graphing a couple. If we have an odd multiple of theta inside sine or cosine, we'll get that odd number of leaves with a period of pi. On the other hand, if we have an even multiple of theta, we'll get double that even number of leaves with a period of 2 pi. And this is important because sometimes we're going to have to find, say, areas or arc lengths of these things, and we need to know where to integrate from. Okay, so we have to be able to break the curve down. So just summarizing what we've discovered here, R equals cosine of A times theta. If A is odd, you get A leaves with a period of pi. On the other hand, if A is even, then you get 2A leaves with a period of 2 pi. Now, just like there's so many different kinds of shapes in rectangular coordinates, there's so many different kinds of shapes in polar coordinates, and we can't possibly do them all. But I'm just going to show you a couple of cute ones, and then we'll do some calculus. We'll do area next. Let's see, back to Desmos. I don't think I need the slider right now. Let's put theta back in there and close the parentheses and add 1. So that's a cute one. Could consider it, you know, a heart or a butt, an apple. Yeah, this is a series of shapes called cardioids. They're supposed to be heart-like. Different things happen when you change that number there. So there's all different kinds of those. If I do something like a fractional multiple, then I get interlocking leaves. And there's wild patterns depending on the relationship between the numerator and the denominator. So if I flip and make it 2/3, I get a pretty different structure. Okay. So one could spend a whole quarter studying these shapes alone. Okay. We're just scratching the surface so we can touch on calculus of polar coordinates. Okay, let's do some calculus. I remember when I first saw those, I'm like, I thought I knew a lot about math. And then I saw this, I was like, oh man, my world is totally blown. There's this whole other world I didn't know existed. I'm sure that's not the end of it, was the next thought. It's too much to know. All right, so let's talk about polar derivatives, and then we'll do area. Now, usually when we do a derivative of a function, here we have something like r equals f of theta. The common thing to do is take the derivative with respect to the independent variable, in which case we're interested in what we call dr d theta, which we could also write as f prime of theta. The question is, what does f prime of theta mean? Well, in words, it's the rate of change of the radius as the angle changes. Okay. All right, let's think about that for a minute. I'm going to draw my slightly redundant x and y axes and call this shape right here, let's say that is one chunk of f of theta. Okay. So we're changing the radius and we're changing the, we're changing the angle, which forces the radius to change, which means we're moving like from some point right there to some point right there. Okay. So some angle theta led to that, some other angle theta led to that, and I have my radii. The angle in between there is what we'd usually call delta theta. So instead of a delta x here, right, we have a delta theta. And the way I drew my picture here, it looks like the second radius is slightly longer than the first radius, which means the radius is increasing. So in that particular region, I would expect to see that dr d theta is greater than 0 because the radius is increasing. And that's all dr d theta tells us. It says, hey, if the derivative is positive, that means your radius is increasing in this region as the angle changes. Okay. Think about that circle graph we did before. Do I have a picture of it here? Yeah. Over here, the radius was 1. But then we start to lose a radius. It starts to drop, right? So we would expect dr d theta in this region to be less than 0 because the radius is shrinking as the angle increases. Okay, let's double check that. What's the derivative of the cosine of theta? It's negative sine, right? So r dr d theta in this example is the opposite of the sine of theta. Sine of theta. If you think about the sine of theta, it is positive from 0 to pi, right? And what were our radii doing here? Well, my radii went from 1 to 0, and then it kept getting more and more negative. So the whole time here, my radius was decreasing as I made that circle. Because this point, when I finished right there, I had an angle of pi, but the radius was -1. So our radius started at 1 and finished at -1. Would you agree that r dropped the whole time? Yeah, okay. At some point, the radius is going to increase if we kept graphing it in the next grouping, okay? Because from pi to pi over 2, the sign is negative, but we're taking the opposite of it. So we would watch the radius increase otherwise as we move through later. So that's what it tells us. In rectangular coordinates, what did the derivative tell us? If we took dy dx, what was it? It was rate of change, but it had a physical meaning though. What was the physical meaning in rectangular coordinates? It was the slope of the tangent line. Yeah, this ain't slope of the tangent line. It's just how the radius increases or not increases. It decreases, or maybe the radius is fixed. Okay, so if we need to find a tangent on a polar curve, this will not do it. Okay. So just a brief note on tangent lines. There's not much math I think is ugly. I think almost all math is beautiful, but tangent lines are slightly ugly. For a couple of reasons. Consider y equals mx plus b. That's a rectangular equation. If I want to convert that to polar, I have to replace y with r sine theta and m with r cosine theta. Okay. Now, generally, in polar coordinates, we write r as a function of theta, which means we have to solve that for theta. It means I have to get all the r's on one side. Oop, equals b, sorry. I can then factor out the r and divide by the remaining portion. So I'm going to skip a step there. If I factor out the r and divide, I will get b divided by whatever's left, which is that, that, and that. So that's supposed to be sine of theta minus m cosine of theta. So this is what a line looks like in polar coordinates. It's a crazy rational function of sines and cosines. Okay, so that's one part of the ugliness. There is, if you dig deeper, it does get slightly beautiful, but it's algebraically and graphically kind of a pain. Next thing to consider, that's a line. How do we find the slope? Well, slope, there's no way around it. Slope is change in y over change in x. Let's see. And we calculated earlier that dy d theta is that crazy thing, and dx d theta is that crazy thing. So to do slope in polar coordinates, we have to take this divided by that. All right. So we won't do this often. I'm going to get back there. So my numerator here is going to be dr d theta times the sine of theta plus r cosine theta divided by dr d theta cosine of theta minus r sine of theta. So whereas that's the first thing we start off with in Calc 1 is slopes of tangent lines because they're not too hard. In polar, they're outrageous. And this would be the m in the equation on the other page. Pretty exciting, huh? So I guess we're not going to get to area today because I need to follow through with an example of this. Going back to that first circle we did, r equals cosine of theta. Let's get a graph in Desmos and see if this works. Okay, so there's our graph right there. At pi over, let's see, right around here was pi over 6. So we're going to find out what does the tangent line look like at pi over 6. So that's going to be this line right there. We're going to attempt to find it. So to do that, we need to first consider the point we're at. And the point we're at is r, remember theta. We usually use a semicolon. Theta was pi over 6. And the cosine of pi over 6 is the square root of 3 over 2. So that's the point we're going to try and find a tangent through. In order to do that, I'm going to need to calculate the slope. And so the slope is this. So I need dr d theta first, which is the negative sine of theta. And at this point, the only theta I care about right now is pi over 6. Right? I don't want to leave that as a function. That's an insane function. So cosine of pi over 6 is square root of 3 over 2. What's the sine of pi over 6? 1/2? Yeah, and I want the opposite of it. So for me, where am I going to write it? Right here. Dr d theta evaluated when theta is pi over 6 is equal to negative 1/2. So I need to now evaluate what the slope is. So dy dx is going to be equal to dr d theta, which is -1/2, times the sine of pi over 6, which is 1/2, plus r at this point is square root of 3 over 2, and cosine of theta is also square root of 3 over 2. In the denominator, we have dr d theta again, so -1/2 cosine of pi over 6 square root of 3 over 2 minus r, which is square root of 3 over 2, and sine of pi over 6 is 1/2. And we got to finish cleaning that sucker up a little bit. Let's copy that over to a new page. Catch it all? Close enough. All right, so again, we're finding dy dx when theta is pi over 6. So what does that give me? It gives me a -1/4 in the top plus 3/4. In the bottom, I can factor out a negative there. So I'm going to put a negative out front. And so then I have the square root of 3 over 2 plus the square root of 3 over 2. So let's see. 1/4 minus 3/4 is 2/4 or 1/2. So I have the opposite of 1/2 over the square root of 3 over 4. Oops, yep. Thank you. 2 times 2 is 4. Okay, so that's square root of 3 over 2. And so then the halves divide out. So it looks like my slope is -1 over the square root of 3. And does it seem reasonable that it's a negative slope for the point we're interested in? Yeah, according to Desmos, we definitely have a negative slope at this point right here. Okay. All right. We've got the slope. We have the point. We don't have the y-intercept, though. We need the y-intercept to use that crazy formula back here. So we have to calculate the y-intercept. So we're going to have to do a little rectangular work here. Normally, we have y equals mx plus b. And so we have to calculate x and y to do that. Excellent. So x, remember, is r cosine theta. R at this point is square root of 3 over 2. And the cosine of pi over 6 is the square root of 3 over 2, which gives me 3/4. And y is r sine theta. R at this point is the square root of 3 over 2. And let's see, sine at pi over 6 is 1/2. And so then we get square root of 3 over 4 is the y value. Okay, so now we know if y is square root of 3 over 4 and m is -1 over the square root of 3 and x is 3 over 4, we can now find b. So adding this guy to the other side, I get square root of 3 over 4 plus 3 over 4 square roots of 3. Now this cleans up a little bit. Oh, this kind of cleans up beautifully. Rationalizing the denominator here, square root of 3 times square root of 3 top and bottom. Square root of 3 times square root of 3 is 3. which cancels with the 3 above. So I have square root of 3 over 4 plus the square root of 3 over 4. So b must be square root of 3 over 2. Okay, now it's time to see if our good work paid off. We have m, we have b, we have a polar version of a line. Let's see what happens. So the polar version of the line, where'd you go? Back here, is going to be b over the sine minus m times the cosine. So I'm going to attempt to write that down. Where are we? I'm running out of room. So our tangent line, let's call it y sub t for tangent, is going to be equal to b, which is the square root of 3 over 2, divided by, now I forgot, it was sine first, minus m. Now our m is negative, so we can make that a plus, 1 over the square root of 3 times the cosine of theta. I think I got that right. Yeah, sine minus m cosine. All right, wish me luck. Whew. All right, so r equals square root of, I guess I don't need parentheses, 3 over 2 divided by sine of theta. Notice just dividing by the sine of theta gives us a horizontal line, plus the cosine of theta. Now that's a line, but the wrong slope, divided by the SQRT of 3. Bang, we nailed it. Oof, man. Okay, so what's the problem with this problem? We're mixing rectangular and polar, which can be very painful sometimes. So this circle could have been expressed in rectangular coordinates. We chose to do in polar. Lines in polar are a pain in the butt. Okay, so would it have been also messy in rectangular? Yeah, it would have been a little messy in rectangular because the square root of a circle is kind of complicated in rectangular too. So we trade complications in one place for complications in another. I think this is probably slightly a difficult problem in polar than rectangular. So we're out of time for fun. Tomorrow what we will address is what area means in polar coordinates, and we'll also get to arc length in polar coordinates. Feel free to jump ahead in the homework if you wishes.